Hello, welcome to the course SJPHY1C01 Properties of Matter and Thermodynamics. The contents of today's lecture is taken from Properties of Matter by J.C. Upadhyay. So far we have completed Module 1 and 3. Today we will start a discussion on Module 2, Surface Tension and Viscosity. In particular, today's class we are going to talk about surface tension. Surface tension is something which we encounter in our daily lives. One of the examples of surface tension is if you take water in a beaker and dip a straw into that, you will find that water is rising in the straw. So this is because of surface tension. Now, what's the mechanism behind this capillary rise? You will get an idea about it probably towards the end of this discussion. Now, first thing you have to understand is that surface tension is a molecular phenomenon. It arises because of the interaction between the molecules of a liquid, which are mediated by various forces. So to have a proper understanding of surface tension, we need to first understand about molecular forces. There are two types of molecular forces, cohesive forces and adhesive forces. Adhesive force is the force of attraction between molecules of different substances. For example, if you sprinkle water onto a glass surface, you will find that some of the water droplets stick to the glass surface. This is because of the adhesive force between water molecules and the glass substrate. On the other hand, if you join two small water droplets, you will find that they together form a large drop. This is because of the force of attraction between the two water molecules. Such a force of attraction between molecules of same substance is known as cohesive force. One thing you have to remember, this is different from gravitational force, because we know that if you take any two objects of mass m1 and m2, there is always a gravitational force of attraction between them, and the force is given by g m1 m2 by r square. Okay, so gravitational force has a 1 over r square dependence. On the other hand, cohesive force has a 1 over r to the power 8 dependence. So these two are completely different. Also, when it comes to molecular dimension, we know that the mass of a molecule is very, very small. Consequently, the gravitational force is going to be very weak. So in molecular dimension, the cohesive force is going to be much more prominent. Okay. Before going into the details of surface tension, we need to get familiarized with certain terminologies. The maximum distance up to which forces of cohesion or adhesion can act between two molecules is known as molecular range. This is typically of the order of few nanometers. As you know, 1 nanometer is 10 to the power minus 9 meter. Now, if you take a molecule and draw a sphere around it with a radius equal to the molecular range, and this sphere is known as sphere of influence. So expectedly, a molecule can attract only those molecules within its sphere of influence. So if you look at this schematic, I have a molecule here and the sphere of influence is indicated by these arrows. So only those molecules within the sphere of influence, they take part in the interaction, and all other molecules outside the sphere of influence, they are completely unperturbed by the presence of this molecule. So when we say molecular interaction, we are essentially talking about the neighboring molecules within the sphere of influence. Now, if you take a liquid in a beaker, for example, water in a beaker, and look at the surface, macroscopically, this presents as a calm and quiet system, like seemingly nothing is happening. But if you happen to have a microscopic view, for example, you take a microscope and zoom into the surface so that you can reach the molecular dimension, then in this microscopic picture you will find that the free surface of a liquid is not very calm. It behaves like a stretched elastic membrane which has a natural tendency to contract so as to assume the smallest area possible. And what's the reason for this? I will explain that in the next slide. So for now, just take it that the free surface of a liquid always has a natural tendency to contract, which means it is always under a state of tension. And this tension is known as surface tension. If you imagine that this is the surface of a liquid, and if you draw an imaginary line AB of length L, so you have molecules on this line. So you have a one-dimensional array of molecules on this line, and since the surface has a natural tendency to contract, what happens is that the molecule on the right side of this line will try to attract this molecule so that the separation distance can be minimized. That's how you contract a surface, right? You separate the distance, you reduce the distance between every point possible, right? So molecule on the right side will attract the molecules on the line. Similarly, the molecules on the left side also will try to attract this molecule. So in other words, the molecules on line AB experience a pulling force towards right as well as left. So if you take the pulling force as F is proportional to the number of molecules on the line, and the number of molecules in turn is proportional to the length of the line L. Also, the force acts perpendicular to the line AB, which is also tangential to the surface. So I can write force F is proportional to L. I can replace the proportionality with a constant T. So I can write F equal to TL, where T is the constant of surface tension. Now from this equation, I can give a definition to surface tension. For example, when L equal to 1, F is equal to T. So surface tension is defined as the tangential force per unit length acting at right angles on either side of an imaginary line drawn on the surface of a liquid in equilibrium. So from this equation, I can write T equal to F by L. The unit of force is Newton, unit of length is meter. So the SI unit of surface tension is Newton per meter. Now, what's the molecular origin of surface tension? The first satisfactory explanation for surface tension was given by a scientist called Laplace, and this is popularly known as Laplace's molecular theory of surface tension. So imagine you have some liquid in a beaker. So let's consider three molecules A, B, and C. The sphere of influence of A is completely inside the liquid, which means it is attracted equally in all directions by other molecules. Hence, the resultant cohesive force acting on it is 0, right? Because for force in any given direction, you have a force in the opposite direction. So these two cancel. So the net cohesive force is 0 in the case of A. On the other hand, if you look at B and C, their sphere of influence is partly outside the liquid surface, which means the number of molecules attracting these in the downward direction is more than the number of molecules attracting them in the upward direction. Consequently, they experience a net downward cohesive force. So all the molecules near to the surface of a liquid experience a net downward force. Now, if you take the surface of the liquid as line PQ, and if I draw a line RS parallel to the surface line PQ at a distance which is equal to the molecular range, then the layer of liquid between PQ and RS is known as the surface film. As I said, all the molecules in the surface film, they are going to experience a net downward force. So you can say all the molecules in the surface film are pulled downward with a net cohesive force. Now with this understanding, let's try to understand the origin of surface tension. Now if I were to bring a molecule to the surface, since there is a net downward force acting in the surface film, I have to do work against this downward force to bring a molecule from inside to the surface. Typically, this work is stored in the molecule in the form of potential energy. So when I bring a molecule from inside to surface, that molecule is going to have some extra potential energy because of this extra work done. In other words, potential energy of molecules in the surface film is greater than the potential energy of the molecules lying below. Now, if you take any system, there is a general principle. If the system wants to have more stability, it needs to decrease the energy. For example, if you take a hydrogen atom, you know that the electron in the hydrogen atom is always in the ground state. Why? Ground state has the least energy, so that it has the maximum stability. If you somehow excite the hydrogen atom by providing some energy, either through thermal means or by shining light on the hydrogen atom, you can excite the electron to a higher energy state. But the higher energy state, since the energy is more, stability is less, so the electron cannot reside in the higher energy state for a long time. After some time, you will find that electron comes back to the ground state, because in ground state, stability is maximum. So this is true for any physical system. So here also, to attain maximum stability, the liquid system should minimize the potential energy. Now the total potential energy is nothing but potential energy of the sum of the potential energy of all these individual molecules. So if you were to decrease the potential energy, you need to decrease the number of molecules in the surface film. Now, how do you decrease the number of molecules in the surface film? There are two options. Either you decrease the thickness of the surface film, but unfortunately the thickness is fixed. The thickness is equal to the molecular range, and for a given liquid the molecular range is a constant. So you cannot change that. So the only option is to decrease the surface area. So every liquid by default has a natural tendency to decrease the potential energy so as to attain maximum stability. In that process, it will try to decrease the surface area. So this is the reason behind the surface tension. So liquid has a natural tendency to contract so as to have lowest possible area. So this is known as Laplace's molecular theory. Now, as I said, potential energy of molecules in the surface film is greater than that of the molecules lying inside the liquid. This excess potential energy per unit area of the surface film is called surface energy. As we know, surface of a liquid is in a state of tension and has a natural tendency to decrease the area. Therefore, if the surface area is to be increased, work needs to be done against the surface tension. This work is stored in the surface as mechanical part of the surface energy. So if you call surface energy as E, it has two components. One is the mechanical part, which is the surface tension, and the remaining part is the thermal part, because if you look at the surface of a liquid, there is constant exchange of heat between the surface and the surrounding so as to keep the temperature constant. So surface energy has the surface tension component as well as the thermal component. So you can have one more definition to surface tension with this understanding. So surface tension is the amount of work done in increasing the surface area of a liquid by unity under isothermal conditions. So this is work done per unit area. So the unit is joule per meter square. One thing you have to note, surface tension is also known as surface free energy, and this is true not only in the case of liquids but also in the case of solids. So in the case of solids, surface free energy is nothing but surface tension of the solid. Okay. So here you can see the surface free energy or surface tension of certain liquids. So water has a surface tension of 72.1 millinewton per meter. On the other hand, oil has much lower surface tension. That's why the capillary rise of oil is smaller compared to that of water. Surface tension plays a very important role in determining the shape of liquid drops. So in general, the shape of the liquid drop is governed by two forces. One is force of gravity and second one force of surface tension. If surface tension alone is acting on the drop, then the potential energy is minimum when surface area is the least. Okay, this we know from the molecular theory. Okay. And from geometry, we know that for a given volume, a sphere has the least surface area. So if surface tension alone is acting, the drop will assume a spherical shape because it will have least potential energy when it assumes a spherical shape. On the other hand, if gravity alone is acting, we know the expression for gravitational potential energy. This is mgh. Mass of the drop is a constant, acceleration due to gravity is a constant. So if the drop wants to minimize the potential energy, the only option is to minimize h. This is the height of the center of gravity. Okay, so in the process of minimizing the potential energy, the drop will bring the center of gravity to the lowest position. In other words, the drop will spread out in order to bring the center of gravity down. Okay. So when surface tension alone is acting, the drop will have a spherical shape. If gravity alone is acting, the drop will have a flatter shape. Okay. But in any realistic scenario, both these forces will be acting on the drop. In that case, what determines the shape? So in such cases, the drop will assume a shape in such a way that the net potential energy due to both the forces is minimum. If you look at the gravitational potential energy mgh, it depends on the mass of the drops. Mass can be written as a product of density ρ and volume v. For a given liquid, density is a constant, so mass depends on the volume. A volume is proportional to cube of linear dimension. For example, if you take a cube of length L, volume is L cube. If you take a sphere of radius R, volume is 4 by 3 pi R cube, right? So volume is always proportional to cube of the linear dimension. On the other hand, if you consider potential energy due to surface tension, we have seen that this is proportional to the surface area of the drop, and surface area is proportional to square of the linear dimension. In the case of cube, it is L square, 6L square actually, and in the case of a sphere, this is 4 pi R square, right? So gravitational potential energy is proportional to square of the linear dimension. Okay. Now, if you take two drops, a large drop and a small drop, let's compare these two potential energies. Imagine that you have a large drop of radius 2 centimeter. Now, the gravitational potential energy is going to be 2 cube, which is 8, and surface tension potential energy, this is equal to 2 square, which is 4. So here you can see in the case of a large drop, gravitational potential energy is dominant compared to surface tension potential energy. Therefore, in the case of large drop, in order to minimize the potential energy, the drop is going to assume a flat shape, because here gravitational potential energy is the dominant force, and to reduce the gravitational potential energy, drop should have a flatter shape. On the other hand, when you consider a small drop of radius 0.2 centimeter, once again let's compute the potential energies. Gravitational potential energy is 0.2 Q, which is 0.008, whereas surface tension potential energy is 0.2 square, which is 0.04. So here you can see that surface tension potential energy is the dominant one. So if the drop wants to have maximum stability, it needs to minimize the surface tension potential energy, and for that it will assume a spherical shape. So large drops always have flatter shapes, whereas small drops will have spherical shape. So this is a practical demonstration of this. These are drops of mercury of different volume. You can see that when the volume is very small, the shape is perfectly spherical, whereas when you increase the volume, when you increase the size of the drop, it becomes more and more flat. So that's for today. Thank you.